So guys, when you transfer $100 to your friend, your balance reduces to $900. But your friends still shows $0. The bank system says total of $1,100. And this actually happened at a major bank in 2023, costing around $10 billion. And the problem is lack of consistency. You miss this in your interview and you'll fail 40% of the distributed systems question. So today we're going to discuss about some of the patterns and problems in algorithm regarding data consistency and consensus. We'll take each one of them and this will cover all the algorithms related to consistency and consensus related to distributed systems. Let's go back to the problem which we discussed initially. So here you see your account has $1,000 and you transfer $100 to your friend's account. Ideally, your account should have $900 left. What if your friend still doesn't receive the money? It is still $0. The bank total says it is $900. Ideally, it should be $1,000. That is 900 plus $100. So the $100 is lost. What is the solution in this case? How do we solve this problem? And this problem is solved by multiple nodes by maintaining the consistency. We have multiple nodes in a distributed system. All the nodes should agree with that value, and based upon that, the value should be updated in the friend's account. This is how the consistency is maintained in different nodes. Let's discuss some of the consistency model here. You've seen Uber app, right? In Uber app, sometimes it shows for the same route $15. Sometimes when you refresh it, it shows $22. And at the same time, your friend standing beside you opens the app for the same route, it shows $18. Three people, three prices, same ride. This is called eventual consistency. And in bank interviews, you need to know when this is acceptable and when it is catastrophic. So there are three types of consistency model. The first one is eventual consistency. Second is strong consistency. The third is linear consistency. So as we move from left to right, eventual consistency is the least consistent but is the fastest. Linearizable system is the strongest form of consistency known till now, but it is the slowest. Let's go through each one of them with an example. In eventual consistency, let's write $15 to node 1. In node 2 and node 3, the value is still $22 and $18. So at that time, if you try to read from these individual nodes, you might receive a stale data. If you read from node 1 where you have written, you'll see $15. But if you read from node 2 or node 3, you'll still see the stale data, that is $22 and $18. Eventually, all the nodes will become same. All of them will have $15, but not at the current moment. And this is called eventual consistency. The consistency is happening eventually, slowly with time. Some of the use cases where we use this is social media likes or the view counts, because likes do not need to show perfectly at that particular moment. They can be increased with time. Now, the next form of consistency is strong consistency. In strong consistency, all nodes are updated immediately. No matter what, they have to be immediate. If I transfer $500 in node 1, they have to be $500 in node 2 and node 3 before the node acknowledges the write. So this is a very useful scenario, and it is particularly used in banking system, inventory system, so that the balance remains consistent in all the nodes. The third and the strongest consistency is linearizability. Oh man, this word itself is a puzzle for me. Whenever I try to call this, it comes out linear. So, but anyhow, let me call it very slowly. Linearizability. This is how you call this word. It's a very difficult word to call, and it's kind of a tongue twister for myself. So in linearizability, the operations appear instantly and total order of all operations are maintained. What do you mean by these two lines? We saw in strong consistency, the value has to be consistent at the same time. But one thing we are missing, the order of the operations. What if in node 2, in the strong consistency phase, before writing $500, there was $100. And in node 1, before writing $500, there was $200. Although they happen at the same time, but the order was not same. Whereas in linearizability, along with the state of the value that is written, the order has to be also same. It cannot be that the order is coming upside down or in reverse order. They has to be also maintained. And the maintaining of order is called causality. We also maintain the causality, how the event happened with time, along with the state that is strongly consistent. Now, this kind of consistency is typically used when you're using distributed logs or leader election using Zookeeper or something like that. Now, I hope you got a pretty much a vague idea about the consistency models. Now, we will deep dive into some of these models that will actually help you crack the fan. Let's talk about linearizability. Suppose you and your friend edit the same Google Doc. You type hello, and then your friend types world. Do you see hello world or you see world hello? Right? You see hello world, not the other way around. Now this is called linearizability. The order of the cause is also maintained along with the consistency. It has the hardest consistency guarantee, and Google, Amazon and Meta will ask you to design this. Okay. In linearizability, the operations appear to execute atomically at single point in time between invocation and response. Let's take an example. Client A reads old data that is equal to 5. At the same time, after that, client B writes 6 and gets an acknowledgement of OK. When client C reads, it should ideally read the new value that is 6. So this is a linearizable execution. What if client C still reads the older value? Then this action is non-linearizable and this violates linearizability. Let's take another example. You must have seen when we do registration of username, how does the system make sure that the username does not exist from previous? For example, when you do registration over Instagram or you register an email ID, how does it make sure that there is no existing username with the same name? This happens because of linearizability. Only one user gets that username, no duplicate registration, and it is consistent across all the servers. This is how a linearizable system is maintained. To implement a linearizable system, we ideally use a single leader system. Whatever client writes or reads has to go through a single leader that is copied to the followers or the replicas, not the other way around. Even the read and the writes, they have to be through the leader. Then only you can have a linearizable system in this case. Now you got to know how we implement the linearizable system, but there are a lot of drawbacks. We have to have a cost for everything. To implement linearizability, we have to have a cost. The time is the main issue. We have a system that is much more slower. What are some of the costs due to which many systems don't implement linearizable system, or they try to avoid this whenever possible? In one of the scenario, let's say there's a network partition. There are two servers, server in US East and server in US West. Now, because of some problem, US East and US West cannot interact with each other. There is a split. Because of this, there comes a condition called split brain, because two different servers can act by themselves. In this case, how do we maintain linearizability? Either we stop all the server's requests, wait for the network to heal, and then we start the operations. Now the result of this is downtime and lost revenue. We definitely cannot use this because in this case the system stops completely. Now the second option. Can we give up linearizability? We want to keep serving the request. We can accept the stale data temporarily. If we can meet these requirements, then why not give up linearizability for availability and follow eventual consistency? But remember this, we can only give linearizability if we can accept the stale data temporarily. Okay, let's take a real world example. So Amazon has a shopping cart. It works even if the stale prices are there. You can add to cart all the products even if the server is not available. This increases the user experience. It makes the user experience better in making the website totally down. In this case, you can choose availability. Now, what about banks? Can we accept old money data or stale data in the banking system? Definitely no. You cannot lose the money. Money is very important. In this case, you cannot choose availability. You have to choose consistency no matter what. So in this case, the ATM should show service unavailable in case of the server is down, but it should not work. Now the cost is that if we are doing linearizable reads, it does the cross-center interaction in 100 milliseconds. And in non-linearizable reads, it is approximately 1 millisecond. So you can choose between non-linearizable and linearizable. The cost is 100x lower service. In interview, always ask, do we need linearizability or not? Because most systems don't need linearizable. Only in special scenarios it will need linearizable. Now, another problem that linearizability handle is the causality and order. Sometimes what happens is you receive a comment under your post. Do you wish to see that comment before the post, or you want to see it in the order and who all has commented? So that does matter, right? It is the causal order. After the post, if you see the comment, it makes sense. If you don't see the post and you see the comment, it's like, what the hell is that? There's no post and I just see the comment. It's a problem. So, right? So that is called causality or causal order. This is one of the most important things we need to discuss in interview, because causal order is very important. In some cases, it might not be important, but in most of the cases nowadays, like for audit trail loggings, we need to maintain the causality. When you post on LinkedIn that I got the job, your friend comments, congratulations, but some people see the comments before the post. Impossible? No, it's possible if there's a causality violation. It happens millions of times per day, and understanding causality will save you in distributed system interviews. There's event A and event B. If event B happens because of event A, this means A causes B. This is causal. As an example, I told you earlier that you post I got the job is an event A, and your friend commenting congrats is an event B. So the event B happened because of event A. So B depends upon A, and this is causally related. Now let's talk about the violation. If the user 1 sees comment before the post, this is wrong order, right? This is called a violation. The correct order should be first you see the post, after that you see the comment. This is the right way of causal consistency. Now, how do you maintain the causal order? There are many solutions there. One of the solution is called Lamport timestamps. You add a timestamp to each of the event that is happening. So you have event A and event B. A causes B. This is the same example which we discussed. You posted that you got a job, it's event A, and then you got a comment from a friend, congrats, that is event B. So A causes B. B is dependent upon A, and this is causally related. Now, if you've got it other way around, violated the causality, and that is the wrong order. The solution for this is causal consistency. We preserve the causality, not the total order. So what we do is post at timestamp 100, and the comment that happened was at timestamp 101. So 101 event depends upon the event that happened at timestamp 100. So the system ensures that the comment never is shown before the post. As a solution, we can use Lamport timestamp. Each event gets a logical timestamp. Every node has a counter. That's a logical counter. They start from value 0. So if there are two nodes, suppose node A and node B, both of them start at counter 0. The first event happened, that is, you posted a job. The timestamp increases to 1 automatically. We increment the timestamp by 1. Now you need to send that timestamp to node B. Now we need to increase the counter for that as well. So what do is we take the max of the current timestamp, that is 1, and the previous timestamp, add 1 to it and increment the counter. So in that case, we do 1 max of 1 comma 0 and add 1 to it, and this becomes 2. Now the current timestamp has 2. We send it to node B with timestamp 2. Now what does what does node B does? Node B receives the message from A with timestamp 2. Now it increments its counter. We'll use the same formula. We'll use the max of current timestamp, that is 0 for node B, and 2 from the message we have received from A. So max of 2 and 0 is 2. Then we add 1 to it, that is 2 plus 1 is equal to 3. And this should be the current timestamp of node B, that is equal to 3. So from 0, it changes to 3, not 1 or 2, because we're using a formula. Take it in mind, we are not simply incrementing it, we are taking the max and adding 1 to it. That is why in node B, the timestamp changes from 0 to 3. Next is total order broadcast. In total order broadcast, we make sure that all the nodes deliver message in the same order. Node 1, node 2, node 3 will have the same order, that M1, M2 and M3, they happen in the same order, not anywhere around. Now the services or the application that use this, where we use total order broadcast, is Apache Kafka or Zookeeper for electing the leader. Now you must be thinking, what about the consistency when we transfer money from one account to another account? How do we maintain that? Do we use Lamport timestamp in that case, or do we use anything else? Well, in that case, we cannot use Lamport timestamp because there still might be some issue with that. So there is one distributed transaction algorithm which is very famous and used in many of the transaction databases. This algorithm is called two-phase commit. So when you transfer $1,000 from bank A to bank B, the money must disappear from A and appear in B atomically. If bank A crashes after deducting, but before bank B adds it, you lose $1,000. So two-phase commit solve this, and it is asked in every distributed transaction interview. That I can give you for sure. Let's discuss what happens in two-phase commit. So the problem is you have to do transfer of money from bank A to bank B, and it has to be an atomic distributed transaction. The participants here are 3. Bank A, bank B, and the third participant is the coordinator or the transaction manager, which sees through that all the transaction happens in order. So two-phase commit has 2 phases. The first phase is prepare and the second phase is commit. What happens in first phase? In first phase, the coordinator, it asks bank A that, can you deduct $1,000? Do you have that balance? It asks bank B, then can you add $1,000 to yourself? Both bank, if they reply yes. If the bank A has a balance of $1,000, it will reply yes. If bank B is available to accept orders or transaction, or it is available, it will reply yes. After both the participants reply yes, then it locks the account and writes to the log that these 2 banks have replied yes. And then the second phase starts. This is a very crucial phase. In this, you do the actual commit. So if you've got all yeses, the coordinator will say commit, and then bank A will deduct $1,000 and bank B will add $1,000. What if the coordinator received no? It will say abort, and bank A and bank B will do a rollback. In the prepare phase, bank A and bank B send yes to the coordinator. Then after that, in the commit phase, bank A and bank B send back done to the coordinator when they have done the deduction and addition of money. Simple. Not much difficult. It is very simple, and it is very efficient also. But this algorithm has a lot of problems. It's super slow. You have to block all the servers. What do you do about it? In this fast-paced world where thousands of transactions are happening, what do? You just happen to hold your head and then think about it. There is another problem with this. There's a single point of failure. What if the coordinator crashes, the system will halt, there will be no transaction happening. And it is super slow because you'll have to wait for all the systems to say yes, and the coordinator will wait till then. Now, because of this problem of the slowness or the blocking part of this, we have another set of algorithms that solves this problem, and that is called consensus algorithm. Now, Google has 10,000 servers. They need to elect one leader. If two servers think that they are the leader, data gets corrupted. And if no server becomes the leader, the system halts. This is the consensus problem, and solving it is worth a PhD. Raft and Paxos are the answer for this. There are two consensus algorithms. In 1989, the first algorithm was proposed as Paxos algorithm. So this was a theoretically proven algorithm. Although it's very complex, but it is still used by Google Chavi. Then in 2014, a revolution happened. A new algorithm came up and which took the market by surprise. Everyone was using Raft, moving away from Paxos because of the complexity. It quickly got adopted within a few couple of years, and there are various applications who are using it, like etcd, console, cockroachdb, zookeeper. Everyone's just now using Raft. In this tutorial, I'll be discussing about the Raft algorithms more because it is widely used instead of Paxos. Paxos is a theoretical subject. Maybe if you want to study about it, you can go to the papers. But I would say you go and study for the Raft. In Raft, we have three roles. One is leader, which handles all the rights. Next is the followers. It replicates from the leader whatever the value is coming, and the candidate. If someone wants to become leader, they become the candidate. How does the leader election happens? First, all the nodes starts as follower. If there is no heartbeat received, because they should receive a heartbeat from a leader. If no heartbeat is received, it means there is no leader. Then one of the node decides that I will become the candidate. I need to fight the election. It requests for vote from all the other followers and it itself also. Once it receives the majority of the votes, that is more than half of the vote, it becomes the leader, and then it starts sending the heartbeat to all the followers so that they know that a new leader has been elected. A client sends to a leader to write x is equal to 5 in this case. Okay? We write x is equal to 5. Now the leader replicates the value to all other followers that x is equal to 5. Once the leader has done the replication, the followers send an acknowledgement to the leader, and then the leader sends a success message to the client after it has got the majority acknowledgement. The acknowledgement can be 3 also. So there are 5 total followers. So it should be 5 by 2, that is equal to 3. If it receives 3 acknowledgement, it is a success for the leader. Now there's a problem. We already discussed about split brain. So if there's a network partition, there are 3 nodes that are present in one cluster. Total there are 5, and there's a network partition happen. Cluster becomes 3 and 2. 3 on one side which cannot communicate with the rest of the 2 nodes, and the 2 this side cannot communicate with the other 3 nodes. Then what happened? This process is called split brain, where there are 2 islands of nodes. One has 3, another has 2. What will happen in this case? They cannot communicate between each other. So this is a problem with the Raft algorithm. So in this case, the island with 3 can actually vote because they have the leader and the majority. But whereas the island with only 2 nodes cannot even vote because they have the minority. So in this case, when a split brain happens, the island with maximum number of nodes can actually do the transaction, whereas the other island will not be working till the time they come up and join the other cluster. This is how we solve the split brain problem. This algorithm is used in Kubernetes. We use console for service discovery. We use cockroachdb and distributed databases. We also use it in Cassandra. Okay, so now Raft powers Kubernetes. The platform is running 95% of the cloud application. Understanding Raft is like having a cheat code for distributed systems interview. Let me show you how it actually works. If you understand the depth of this algorithm, you'll practically be able to solve any system design interview question. Okay, in Raft, we have terms. Whenever a new leader is elected, that is called a term, and the term increments by number 1. So first, if you see in an election cycle, leader A was the leader, that is term 1. When leader B becomes a leader, maybe A crashed or it timed out, that is termed as term number 2. When another leader comes up, so for example, leader C comes up, this is called term number 3. Now this is the definition term. Whenever a new leader is elected, we have a term for them. How does the election process happens? Let's say we have around 5 followers, okay? one of them becomes a candidate and it converts to C1. After converting to C1, there is a voting process that happens. C1 sends message to all the followers, F2, F3, F4, F5, and it asks them that please vote for me. So it goes for a election campaign like it happens with the election campaign in our country as well. It goes to each house, asks them for the vote. And if the followers agree with him, they vote for him. And once the candidate C1 gets the majority vote, that is more than half, it becomes the new leader. So once it gets 3 out of 5 votes, it becomes the leader. And it is now labeled as L1. So the C1 changes to L1 after it receives the maximum number of votes. Similar sense, let me take an example for similarly, how does Raft algorithm works when log replication happens? Let's see how Raft plays part in the log replication process. So the client wants to set the value of x is equal to 5. Got it? That should be fine. So it sends the leader. Now here are the leader logs. We have in the first, it has x equal to 1, second times time it has x equal to 3, and the third times time it has x equal to 5. That is a new entry which is set by the client. Now the x value has been changed to 5. Now what the leader does, it appends the entry x equal to 5 in all the followers. It sends a request to follower 2, 3, 4, and 5. Now once it receives the acknowledgement that from at least 3 out of 5 followers that the log has been committed, it is a success. It sends a success statement for the client. Now because of this, there is a safety guarantee. The committed entry will never be lost because it has been committed by majority of the followers. You get this, right? So what if a network partition happens? In that case also, the left side has 3 nodes and the right side has 2 nodes, right? So the left side having the majority number can commit because it has a majority, whereas the right side does not have a majority. It has only 2 out of 5. So in that case, they cannot commit. So whenever the partition heals and F4 and F5 come back and they are connected to the other nodes, they form the followers of the new system. Simple as that. And the sync logs, and then the sync log from the leader that was already there, that is L1. So whenever they come up, when the followers come up after the network partition has been solved, they will sync up with the leader. Simple. So this is how you solve the problem of network partition in that. Now we discussed about the algorithm, that how we do a consensus algorithm. But do you know how does a banking system and how does a social media platform choose which type of algorithm they want to maintain? How the data should be transitioned? What is the consistency and availability? This is the most basics about the consistency in a distributed system. You can either have a consistency or availability or partition tolerance. You can only pick 2 among them, and this is called CAP theorem, and it is the most essential and fundamental algorithm for a distributed systems. Without this, you cannot solve any distributed system problem. And do you know what? It is the most misunderstood concept in distributed system. So let's get this right and you'll be impressed by this, how it actually works. And that way you can also impress your interviewer. Now in CAP algorithm, we have 3 pillars: consistency, availability, and partition tolerance. Consistency means that all the nodes see same data. Availability means that every request gets a response. Partition tolerance means that the system should work even if there is a network failure. Now you know that partition failure will happen. You cannot avoid this. System might fail. There are so many servers. There can be a natural calamity. There should be a system failure or a hard drive failure. There can be fire. So partition failure is bound to happen. So you cannot choose. You do not have the luxury to choose partition tolerance. That has to happen. Now because of that, you can only choose between either C or A. Either you can choose a system that is CP or you can choose a system that is AP. Now if it is a CP system, it means that it is consistent with partition tolerance. And if it is AP, it means that it is available with partition tolerance. So if we choose a CP system, in that case, if the server goes down, then we need to show server unavailability. This is how the ATM works. Whenever the server is down, you must have seen the server is down. If you go to government office, they always say server is down, server is down. Why is that? It is a consistency partition system. If the server is down, they cannot change anything. Availability takes the lower priority in that case. Then what about the availability system, AP system? They're okay to give you the stale data. For example, if you go to Amazon shopping cart, they're okay to give you the stale prices for some time because the server is down. Because you've seen that if the price fluctuates, after some time they ask you for more money, right? So this is AP system. They're okay with the stale data. That's fine with them. So in interview, you should always ask, can we tolerate the stale reads? If no, then you choose CP, that is for banking or inventory. And if it is yes, then you choose AP, social media analytics. So these are the questions you must ask in an interview. So cool, we've discussed so many concepts related to consistency and consensus, and now we feel like a Yoda monk of data consistency and consensus. Now let's take a real world example that will be using all the concepts which we have used today. Here's a question. The question is, design a distributed log service like Zookeeper that guarantees only one client holds a log at a time, even during the network partition. So let me show you this winning answer. So we should first ask the requirements. According to the requirements, only one client holds a log at a time. Then it works during network partition also. You should write this down during the interview itself. Then we should write that fault tolerant, that if a node failures, then also the system should be available. There should be low latency for lock acquisition. It would be fast enough. We should not take much time for lock acquisition. And that makes sense because if it is slow, then there's no point of doing a system design. All right, let's go to a high level design. So we will have client 1, client 2, client 3. You will always take the Raft algorithm because you have multiple partitions and then there might be 5 nodes. So in that case, we will elect one leader and other 4 nodes will become the follower. And this way we will copy the data or transfer the data during the lock acquisition. Now, how does a lock acquisition happen? First, client 1 sends the leader to acquire a lock on resource A. The leader then creates a log entry within itself that resource A lock is required in the client 1, and then the followers replicate the data in the log entry as well. Once the leader receives the acknowledgement from all the followers, or maybe the majority of the followers, not all the followers, but majority of the followers, then the leader sends to the client that the lock has been acquired. This way it is the majority of the followers. What do we do when we want to release the lock? We follow the same process. The client sent release log of resource A. The leader makes a log entry, sends it to a follower. After receiving the majority of the acknowledgement, it sends a message lock release, and this is how we release the lock. Now there can be failures in this case. What if the client crashes? What if the leader crashes? Now if the client crashes, then there will be a session timeout because then it will wait for some time. If there is no heartbeat received, we will automatically release the log so that others can use the log, other clients can use the log. What if the leader crashes? Then using the Raft, we will elect a new leader so that the lock is not lost, even the data is not lost. So we'll persist the state of the lock in that case. What if the network partition happened? We discussed about the condition where 3:2 network partition happens, and we will choose the partition where there is majority and the leader, and once the minority one comes up, it will join the quorum and then act as one unit. So this way it will prevent any split brains and only one lock holder is guaranteed. Now the question comes, the interviewer asks, how can we optimize this approach? Because there are so many partitions that we need to happen. This is a 5 nodes partition, but there can be thousands of partitions. How do we handle it? Now to handle this scenario, we can optimize it by making 2 different types of lock. We won't have one lock. We'll have one is write log and one is read log. Write log is exclusive log. If a write log is acquired, then nobody can read through it in that case and nobody can write. But what if read log is acquired? If read log is acquired, they can, simultaneously read. Multiple clients can acquire a read log and read simultaneously, concurrently. That way, we can increase the efficiency of the system. And what about condition in the lock acquisition? In that case, we will put it in a FIFO order. Whichever comes first will get the first priority for the lock acquisition. So the final design will be, there will be a client library which will have the session management. It will send heartbeat to the leader and there will be a retry logic. Then there will be a Raft consensus layer which will have leader election, log replication, and majority quorum. And then there is a persistent storage where we store the state of the log, we store the state of the session, and then the replicated logs. So these are the high level design, then client library, Raft, and persistent storage. And this is how we will solve the distributed logs problem. So key decision in this case is we will take a CP system because consistency is the priority over availability in here. We have to have the log at the consistent state. We'll use Raft algorithm. We'll use session-based log that get timed out if it is hold for a long time. We'll have a majority quorum, and then there will be a watch mechanism. This is exactly how the zookeeper works. After this, you can have some follow-up questions. Interview can ask, how do you handle the clock skew? We discussed about Lamport timestamp, right? So you can tell about that. How do we use Lamport timestamp? What if a client holds a log forever? Then we discuss about session timeout with the heartbeat. You can tell about that. How do you implement read or write logs? You can have separate two logs so that we can have optimization to the performance. What if we ask you what's the latency for log acquisition? So it will be 2 round trips for the majority. One round is send the writes to all the leader and the follower, and second is get the acknowledgement and send back to the client. Now what about the number of nodes? In this case, whenever we have a quorum, the number of nodes has to be odd numbers. It always has to be odd number, then only we can have a majority selection. So it can be either 3, 5, 7, 9, 11, 15, all the odd numbers depending upon how many nodes you have. So guys, this is how we solve all the consistency and consensus problem. And now if you know all these by heart, you can solve any distributed system problem. And that is from the experience, because we discuss about this from day-to-day life in every architectural discussion we have. So if you don't know about this, you will be having a very tough time in office itself, because these are the basics which you should know. And being a principal engineer myself, I have to know this algorithm to be able to answer the tougher questions. I will see you in the next discussion where we take more system design questions.